So today's program is to really do the general case. We did n equal to 1 and n equal to 2 yesterday, which was just heating up. So n equal to three particles on the periodic lattice is really the core of the Bethe Ansatz. I will do it in details. And then there is a general n case. So I don't know if I am courageous enough and you are courageous enough, I can really do the general case completely. It's heavy. One has to go through heavy things like what Satya did now. I mean, deriving the Wigner-Dyson formula for eigenvalues. It's a bit heavy, but there's no other way. I mean, so it's going to be a bit heavy, but okay, let's do it. And if you have any questions, just ask me. If you don't understand something, if you don't see something, just ask. Okay, so you remember yesterday n equal to 1, very easy. Just one particle on the ring. N equal to 2, slightly more difficult, because we had this special case where the two particles were sitting next to each other, and there we had some cancellation condition to be fulfilled. That's frightening. Is it okay? Yes? Not quite. Well, okay. So yeah, this is cancellation condition to be fulfilled, and this can be done only. It looks more and more like a disco, your thing, you know. And it's not more a physics school. It's okay. So now let's do the three cases. So just to save some time, I wrote the generic equation. The general case, three particles on a ring. I have no space to draw the ring. And in the generic case, you suppose that they are far from each other. Far means that there's at least one hole in between. Don't take this notation seriously. Just mean that they are well separated and there is no hindrance for the jumps. Each of them can jump without meeting the other. So this is the generic case. But now there is a problem when particles become neighbors. And one has to be very careful. This can happen in different ways. For example, you can have particles, remember that x1, x2, and x3 are in this order. x1 is less than x2, less than x3. So either x1 and x2 are close to each other, and x3 is far apart, and it's kind of spectator. I'm going to write it clearly. Or, I don't know if you can see here, but it's a similar case. x2 and x3 are close to each other, and x1 is far behind. And I'm not thinking boundary condition yet, so there's no question of x3 being close to x1. Just think that it's a very long, very large lattice. So here I would have to write a special equation. Okay, some of these terms vanish. I will not write it because, as I said yesterday, we shall impose the generic equation everywhere. And instead of writing a special equation here, we shall write cancellation equation. So let's write the cancellation equation. So the cancellation equation here, if I'm not wrong, would look like P of, so instead of writing x1 and x2 because they're next to each other, I call x1 x, x2 is x plus 1, and x3 is something. So it will look like that, x, x3, plus q psi of x plus 1, x3. x3 really plays no role here. Minus e plus q psi of x plus 1, x3 equal to 0. This is exactly the same condition as yesterday, exactly the same for the two, n equal to 2 case, but when one more index, which is just dummy. Here? No, I don't think so. Okay, I can always make mistakes. I mean, everybody can make mistakes, particularly me, but I don't think so. Just like that it's the same as yesterday. Okay, here it will be exactly the same type of condition, but x1 will be dummy. And I decide to call x2 equal to x and x3 equal to x plus 1. So again, this is very systematic. I will get but let's go to it. Plus 2 psi of x1 again, which is just complete dummy. X plus 1 minus p plus q psi x1 x plus equal to 0. Okay, if this was all, we would be happy. It would look very much the same as what we have for n equal to 2, and everything would be best in the rest of words. But there is one more thing. that may happen, and probably you can guess what can happen. The three particles sit next to each other, so this is the worst case, but of course one has to take that into account. So this is the so-called three particle collisions. It's a very important case. Three body collisions, three particle collisions. And there the cancellation condition will be more complicated because now you have more hindrances for the jump. The middle particle cannot jump at all, neither forward nor backward. The particle on the left cannot jump forward, the particle on the right cannot jump backward. So here you had the cancellation condition where there was, you see there here you have 9 terms if you wish. Here 3 were missing, here 3 were missing, now 6 terms will be missing. So if we write things again very carefully, the triple collision, so again now they are just standing next to each other. 1 here, 2 is here, 3 is here. Let's call it x plus 1, x plus 2. Okay. And if we write the missing terms and input that they are 0, we shall find what? We shall find that 6 terms have to cancel each other, again just by exception. This term plus this one, okay, plus q times psi of x plus 1, x plus 1, x plus 2. Correct the mistakes if there is any. X plus 2, x plus 2, minus p plus q psi of x, x plus 1, x plus 2, minus p plus q. Okay, I wrote it twice. It's twice, but you'll see why. It's the same one, of course. I could have put 2 equal to 0. This is the cancellation condition for triple collisions. Okay? It really comes by imposing the generic equation for x1 equal to x, x2 equal to x plus 1, x3 equal to x plus 2, and looking at what is missing. I'm sorry? Yes. And I recall y equal to x plus 1, and I did the same thing, you're right, I could have. But I tried to be pedagogical, it's not always the case, but I tried. So you'll see why I chose that. First I could have written it, the middle one x, next one plus 1, but you'll see I did that. So you know this is a kind of catastrophe, because look at what's happening. I know 3 body collisions. If I have 4 particles, so 4 particles, I could have 2 collision and 2 spectacle. 2 collisions, or 3 and 1, or 1 and 2, or 4. If I have 25 particles, it will become less. All possible particles, even with the order, it can be different. If you have a group, the number of special conditions will just become out of control. But this is one miracle, and this is just the miracle, the central point of Bethe Ansatz. The key thing that if you stare at this cancellation condition and you look at it very carefully, you can see that it's just a linear combination of the 2 body cancellation condition. So of course this I'm going to do very precisely. So the thing is, if you look at this term with a b in front of it, this term with a q in front of it, and of course this term, the yellow bigger term, this is just this equation, if I'm not wrong, by taking x is equal to x plus 1, and x1 is equal to x. Just the same. So if you impose that for all values of x1 and x, in particular, this thing automatically vanishes. Is it clear for everybody? Because this is just the key point. This is just the miracle. I mean, integrability is here. Once more. I have 2 body cancellation condition, I have 1 more cancellation conditions, but the 3 guys are sitting next to each other. And if more than 3 to become more and more complicated. But now the miracle is that this cancellation condition is in fact built from these two body collisions. Because the thing that I put into yellow wiggle is exactly this equation, this one. But for x1, don't forget, this is a general formula for any x and x1. So now if I substitute x1 is equal to x, and x is equal to x plus 1, I get exactly the yellow thing. Okay? So if this is satisfied, half of this thing goes out, and of course you can guess the rest. The the remaining terms here, again with the P and the Q, are just one special occurrence of this equation. You can just make them by choosing what? X3 is equal to x plus 2, I imagine. I'm too close to the, yes, yeah, I think it's the case. So if you substitute here x3 is equal to x plus 2, you get the red things automatically vanish. And if you do a little, if you use this equation and do a little change of naming, you get this equation. So this is the absolute key point. It looks like a completely stupid remark, completely trivial. It's totally non-trivial, but this is what they call the three particle conditions factorize into, there's no real factorization, it's rather a sum, but that's how people call it, into two body conditions. So this just tells you that more particle you add, you're not complicating the system further. If you satisfy the two body collisions conditions, then automatically higher, more complicated cancellation conditions will be automatically satisfied. Okay? So this is really the key observation of Bethe. And the whole, really without exaggerating, the whole theory of integrable systems, an exactly solvable model, rests upon this kind of behavior. What people say, that, I mean, collisions, people used to call that S matrix in quantum mechanics words, so old particle physics, and this is called the S matrix factorization. So this is just the key point. Okay? So in fact, the three particle collisions are automatically satisfied. We just don't need to take them into account. We have enough with two-body cancellations. Yeah, as Satya was saying, you're going too fast. But yes, I'm not going to prove it formally, but you can check it. It will always factorize. Where is the catch? So here I just show you the catch in a very pedantic, I don't know the word in English, in a very pedestrian way, very, writing equations. And in fact, if you want to do things in a very formal way, which I'm not going to do at all, first of all, because I'm not a specialist of abstract Bethe Ansatz, but rather a user, I want to do calculations with the equations. I really want to show you how to use them to calculate things. But this is the thing which is hidden behind this Young-Baxter equation. If you know about them, there's a very abstract way of formulating things and writing these conditions as some kind of matrix relations, and this factorization can be put into a very algebraic form, but I'm not going to tell you about that. Okay. So now let's do the Bethe Ansatz, but this is the key point, is that we just don't need this equation. And this is really fortunate, because if you do a kind of counting argument, you will see that already with that you have enough conditions. And if this was not independent, we could not progress. It would block. It would be overdetermined, and there would be no solutions. So it's really fortunate that we're not adding any new condition, because otherwise it's dead. So in fact, it could stop here. It's not the case for the exclusion process because it factorizes. But if you try to solve exactly a system, for n equal to 1, usually it's trivial. It's a one-body problem. N equal to 2, it's quasi-trivial because usually you can go to the relative frame and just write an effective one-body problem in terms of the difference of the two positions, x1 minus x2. And the real troubles start at n equal to 3. And here for n equal to 3, either it goes through or it just stops. And if it stops, your system is not integrable and you have to do other things. Perturbation theory, numerics, mean field, I don't know, whatever you like, but at least the whole integrable system framework just breaks down. So it's just binary. I mean, it works or it doesn't work. So I can just remove that. Now that I hope I have convinced you that this does not add anything new, fortunately. And now we can go to the Bethe Ansatz. So we have to solve this generic equation, which is nothing but a kind of discrete Laplace equation, if you want, biased with P and Q. If P and Q were equal to 1, both of them, this would be just a discrete Laplacian on the line. And we know how to solve that, plane waves. Okay, no other way. And we have to impose these special boundary conditions, cancellation conditions, call them whatever you like. So, of course, we'll do the same procedure as yesterday. First, try to solve the generic case. So, 3 plane waves, exponential ik1 x1, ik2 x2, ik3 x3, with some amplitude. But people don't write that usually like that. I don't know why. And again, it depends on communities. Exponential ik1, people prefer to write it z. Just a change of notation. Just call it z. k1 is z1, k2 is z2, k3 is z3. So people write it like that. It's exactly the same thing. But we know that the generic solution in plane waves is just z1 x1, z2 x2, z3 x3. Okay? Plane waves. And of course, the associated energy is given by E equal to P 1 over Z1, 1 over Z2, 1 over Z3. It's just a generalization of yesterday. Plus Q Z1 plus Z2 plus Z3 minus 3P plus Q. Sorry?
Psi xx, x3, is there a possibility that it will be non-zero?
Let's proceed. If I just take this solution, no way of solving the boundary conditions, as yesterday. It will just block. And then comes again, the same thing, but pedagogy is the art of repetition, I think. That's what I heard one day. You observe that E is invariant if you permute Z1, Z2, and Z3. Any exchange of Z1 and Z2 and Z3 will let this thing completely invariant. Okay? So in fact, I'm perfectly allowed. You can say that this is threefold that generate this energy level by any permutation of Z1, Z2, and Z3. So I can add 6 terms, because they all contribute to the same energy level. So that's when it starts becoming really heavy. But okay, let's do it. So I call this A1, 1, 2, 3 is just the order of the permutation. And now I have to write the 6 other terms. I'm not sure I'll be patient enough to write all of them, but okay, Z1, X1. Now Z3 is at the second position. So I'm not changing the order of X1, X2, X3, but changing the Z's. I could have done it the other way around. Z2, X3, and so on. So there are 6 terms. Yeah, okay. Z2, X1, Z1, X2, Z3, X3. You really want me to write the 6 terms, or it's okay? No. Plus blah, blah, blah. So there would be a term in A, 2, 3, 1, a term in A, 3, 1, 2, and the last one, A, 3, 2, 1, Z3, X1, Z2, X2, and Z1, X3. Just fill the gaps here. Okay? There are 3 terms, 6 terms now. And now the idea is that you can fix the relative value of the amplitudes. The overall constant is not important. It's a linear equation. So you can fix the relative value of these A's by trying to impose the cancellation conditions. Okay? So, okay, maybe I will do that because somebody asked me a question and yeah, there is a small argument here. Okay, but this is heavy to write. So the right way to write it, the correct way to write it is not at all like that because it will become more and more awkward. The right way to write this thing is to introduce the permutation group of 3 elements I'll just explain in a second. So sigma is one of the 6 permutations possible for 3 elements: identity, transposition, and circular permutations. And A sigma just labels the amplitude of the permutation. Is this notation okay? Yeah, so sigma can be the identity. Sigma for 1, 2, 3 goes to 1, 2, 3. I don't remember which I wrote after that. 1, 3, 2. So this is just a transposition between 2 and 3, and so on and so on. Okay? So there are 6 of them. 6 permutations of 3 elements. Okay? And this thing is the group. So sigma n is the group permutations with factorial n cardinality. Okay? So now let's try to impose the constraints. For example, let's try to impose the first one, and then the second one will be the same, and so on and so on. So you just substitute. So just substitute this formula. This is psi of x1, x2, x3 here. Here. So what is it going to give to you? I will remove that. So you have to write each of the 3 terms, and this will give you P sum over the configurations, or sum over the permutations, A sigma Z sigma 1 x, Z sigma 2 x, Z sigma 3 x3, okay, plus Q sigma and sigma 3, A sigma Z sigma 1 x plus 1, Z sigma 2 x plus 1, Z sigma 3 x 3 plus minus P plus Q, the thing itself, or equal to P plus Q A sigma Z sigma x1, sigma 2 x2, sigma 3 x3 with x1, x1, x3, x plus 1, and x3. Okay? So now comes another little trick, but which is important. So here you have monomials in Z1, Z2, Z3. Generically, Z1, Z2, these are permutations of Z1, Z2, Z3. Z1, Z2, Z3 are different. They're all different. Okay? So here you have 6 terms. Here you have 6 terms. And here you have 6 terms. This equation has to be valid for any values of x and x3. Okay? So you have to use an argument of freedom or independence of these monomials. Because how can I say that? If I have lambda and mu, two, this is just a kind of reminder. If I have two reals, lambda and mu, which are different, and I have this alpha or A1 plus A2, how can I say that? I don't even know how to say that. Mu to the power x, lambda to the power y. If this is true for all x and y, and lambda and mu are different, these things have to vanish separately. Okay? Because lambda and mu are different, so there are different power laws, and different power laws are linearly independent in the space of functions. So this is a key point. So here, for example, if you fix sigma 3, so z sigma 3 is fixed, so sigma 3 can take any value from 1 to 3. So this function is just a spectator. Then you have to look, you have to gather terms which have the same z sigma 1 and the same z sigma 2 and cancel them together. Is this clear? This is maybe slightly, is it clear for everybody, or no, it's not here, because I feel it's not clear. Yeah. So how can I do that without writing it completely? I think I will have to write it fully. So I will have again this term. I'm sorry? Yes. Yeah. You're following. I did it on purpose, of course. So 2, 1, yeah. So again, similar kind of yoga. It will be exactly the same term, you can see, but z1, z2 will just appear as a factor, because I have x plus 1, x plus 1. Okay? So it's just exactly the same term, but with, okay, it's xx, sorry, xx, x1 and x2 is xx, and the other term here will be x plus 1, x plus 1. So it's the same term. You agree with me? Yes? So I will have just, if I don't want to rewrite it, I will have this. Okay? This term will give this z1 x1, z2 x2, or z2x, sorry. If I just write this term, I will have x plus 1 instead of xx. So it's exactly the same thing. So I can just put it there and remove this thing. And this has to be equal to, because again z3 is independent from z1 and z2, so I just identify the z3 terms together, and this gives me, so again this is x plus 1, so it will give me, so it will give me what? A, 1, 2, 3, z2 plus A 1, 3, 1, no, 2, 1, 3, z1, p plus q times the same guy, times what I'm doing here. Okay, let's do it completely. Z3 x3 Z. I'm sorry? I'm not audible? Oh, sorry. Okay. So you have heard nothing since I began? That's a total catastrophe. I'm not going to do it again. I mean, as you can see, it's already a nightmare. So it's x plus 1, and z2x, z1, x plus 1. So I've just copied the part of this equation for which sigma 3 is equal to 3. And there will be 2 terms from each sum. Okay? And now I argue that, first of all, this equation is valid for all values of x and all values of x3. And generically, z1, z2, and z3 are independent. Okay? So it means first that, of course, I can cancel that. And if you look precisely, well, there's a z1, z2 to the power x, which goes away, which I can simplify. z2 will come here, and z1 will come here. So this gives me one relation between the amplitudes. Okay? So if I fix sigma 3 equal to 3, this will give me the ratio of A1. Let's call this the identity. This is the basic term. So this will give me the ratio of A213 over A123. Okay? And in fact, you can do that by fixing any value of sigma 3, or fixing any value of sigma 1, or any value of sigma 2. And in the end, if you do things carefully, which I'm probably not completely doing here, well, let's do things in a very abstract way. We'll end up with an equation which will be of this form. I have 2 body collisions. So in fact, I will have the ratio. What kind of ratio will I have generically? Well, I will have the 6 ratios, in fact. Yeah, I will have, in fact, the ratio of any 2, if I have A1, 2, 3, A2, 1, 3, A1, 3, 2, A. So should I proceed? Yes? Okay. So I hope you are convinced, more or less, that this will give me the ratio of any of these 2 amplitudes. Fixing one and letting the 2 other ones just switch between the 2 permutations. So this is one example, but I can have all the ratios. Okay, so in particular, I can calculate the ratio of any A sigma just by taking products with the basic one, the first one, A1, 2, 3. So all the amplitudes are determined. Okay? So here there's a little thing maybe that I want to add if I find my notes, because it's always better to have notes. Again, you see, I'm not doing it in a very formal way, but it's full of algebra hidden, full of permutation groups and all these things. And you can tell me, okay, but you know, I don't know. For example, to go from here to here, I have to permute these 2 guys. And to go from here to here, well, I can do it in different ways. For example, I can permute these 2 and fix, maybe not, or maybe to go from here to here. I can fix sigma 2 and switch 1 and 3. Or maybe I could go in a much more, I don't know, much more complicated way. I could go from here to here, and then switch 3 and 2, and then switch 2 and 1. I don't know, I can do it. I have different paths. Okay? So for example, there is one one thing which is typical, to go from the identity to 1, 3, 2, 1, I could go to A 2, 1, 3, then to A, I don't know what, probably 3, 1, 2, and then exchange 2 and 1, okay? Or I can choose a different path and go to exchange 2 and 3 first, 3, 2, then exchange 1 and 2, and then get here by exchanging 2 and 3. The only thing I'm allowed to do in this fixing and identification is to switch 2 and fix the others. Here there's only one other, but I can do it in different ways. Okay, so you see there are different paths to go from here to here. Is it clear? But of course you have to get the same result. I mean, suppose I choose to go from A to calculate this guy by calculating this one over this one over this one, and then this one over this one. So I get this one as a function of this one, which can be fixed to equal to 1 because there is an overall constant. But I could also compute this ratio, and this ratio, and get this one as a function of this one. This has to give the same result. Yes? So again, you have a lot of algebra which is hidden. So this relation is called a diamond relation, because it looks like a diamond. Relation. And it has to be satisfied. Okay? The nice thing is that you can say, okay, each time I have a new constraint, it's becoming more and more complicated. Unfortunately, it's not the case. This diamond relation is again just the same thing as the cancellation, the two-body collision and the three-body collision, which is just a linear combination of the two-body collisions. And all this is the same thing if you put it algebraically as the Young-Baxter equation. I'm just giving the names. I'm not writing the equation. But this can be put in an algebraic form. Because you can say that computing this as a function of this is a kind of operator. It's a kind of linear operator. And this as a function of this is another operator. So you have a relation between operators. So there's a very formal algebraic way of putting that into a kind of framework. But it works. And here it's trivial. You can just check trivially it works because you have just rational functions, ratios of two things, as I wrote yesterday. Okay? And you can just by looking, see that in fact the ratios are such that things just go through. It's just trivial. So maybe I can write to you one of these ratios, which is the simplest. Again, one has to choose the nicest and the simplest thing. For example, yes, just write one of them. So I think this is the one I chose to write. Yes. So this ratio, for example, is equal to minus P minus Z2 plus Q Z1, Z2. Z3 is a pure spectator here. P minus Z1 plus Q Z1, Z2. And in fact, all the ratios will look like that. The ratios will just involve the guys which are switched. Okay? The spectator will not play any role here. And then you have to remember that, I don't know, there's a trick to remember that you will figure out by yourself. Probably the guy which is, the first one comes here and the second one comes here, or something like that. So more generally, I think I'm not going to do the n, the usual escape. You leave the complicated things as an exercise to the audience, but in fact it's not much more complicated. If I take now n particles on the ring, believe me that only two-body collisions will matter. If we take only two-body collisions, it means that n minus 2 particles are just spectators. So you can fix the value of sigma for n minus 2 of them, and only 2 are switching. Okay? I need 2 of them, and it will give you exactly the same kind of algebra, but it's of course more complicated. It's longer to write, but it's not more complicated. We have z sigma n to the power xn, and the general relation between two amplitudes of the Bethe Ansatz, the very, very general relation, can be written like that, if I'm not mistaken. You take any a sigma, so any amplitude corresponding to the permutation sigma, you permute I and I plus 1, and this will give you minus, so exactly the same kind of ratio, P. Oh, sorry, I made a small mistake here. It's a normalization mistake. There is a P plus Q here. Often I normalize P plus Q equal to 1. So it's P minus P plus Q Z sigma I plus 1 plus Q, the product, and the same thing here, but of course the other one. Okay, so this shows you that the two-body cancellation conditions in which only two particles interact are enough to fix all ratios of amplitudes. So it's really fortunate that higher collisions do not impose new conditions, because you have no freedom now anymore. And don't forget, there is an overall constant which is not important, because these are linear equations, and you know the ratio of any two of them, especially you know the ratio of any A sigma with A1, 1, 2, 3, n, A identity. So you have no freedom anymore. And if you had any new cancellation condition which had appeared because of some reason, Bethe Ansatz would fail. So it's just tight. Okay. So we are not totally done yet. Yes? You're right. So I have to finish by putting the periodic boundary condition. That's exactly, we are not done yet. We have to impose the periodicity. Okay? So this would work for an infinite lattice, but I have to impose a periodic boundary condition. So the periodic boundary condition as you remember from yesterday, this periodic boundary condition tells you that psi of, again I prefer to take my notes so that I don't change the notation and then it becomes a nightmare. So psi of x1, x2, xn can be obtained by making x1 go through the site number L. So this is one way of writing the periodic boundary condition. Maybe yesterday I just changed the names and I called that x1, x2, but these are them in variables. But it's just the same. Okay. And now you have to substitute the Bethe Ansatz form into that equation. Okay. So if we do that, well, let's do it for 3 because it's a bit heavy for n. But it's the same, exactly the same thing. Let's do it for 3. It just tells you that sum over sigma A sigma Z sigma 3 to the power L. Okay, so here I just I wrote it the other way. Okay, sorry for that. It's perfectly equivalent, of course, but you know, when you prepare a lecture, it's always easier to stick to your notations. Otherwise, can end up tragically. Again, it's just a change of names of the variables, but just to be consistent. So I just take n equal to 3 and do the exercise. So of course it will make x3 plus L. So I just put it here. And this has to be equal to sum over sigma A sigma Z sigma 1 to x3 Z sigma 2. So this is this thing, x2 x1 x2. So this is psi of x3 x2 x1, and this is psi of x1 x2 x3 plus L. Just substitution, okay? Just substitute the general form into that equation. And now again I have to do some identifications using independence of these monomials. And you see this identification, well, so there's a little trick here. You can do it in a very you can do the identification by writing the things and in a very pedestrian way, but there is a more efficient way of doing it. So you see here the order is not the same. I mean, I have sigma 1 x1, sigma 2 x2, sigma 3 x3, but I have a sigma 1 x3, sigma 2 x1, and sigma 1 x2. It would be much better if I had the same indices to identify. It would be much more efficient. Yes? But of course I don't have the same. But now here comes the little trick. This is the sum of all permutations. Okay? So it's a sum over this group of permutations. So instead of taking these permutations, how can I explain that to you? This group is invariant by multiplication by any element of the group. How can I say? Okay, let's be very abstract. Nothing to do with Bethe Ansatz. Sometimes it's useful to be very abstract. I have a group G, and I'm summing some function. It's a finite group, and I have elements in this group. And I'm summing some numerical function. There is a function which is a numerical function, which I can evaluate on all the elements of this group. It has different values, okay? And I just want to compute this sum. It can happen. I don't know. I have the group. What kind of group do you like? I mean, any group you wish. I mean, give me an example of a group, of a finite group. What is your favorite finite group? Huh? No, it's not finite. Rotation is really anything. Any group, I don't know, the group of symmetries of the square or the cube. So it has a finite number of elements. And for each element which leaves the square invariant, I have a number which is attached to it. Well, this sum is equal to the same sum if I have any element, G0, special element, not the identity, but this is equal to this. Do you agree with that? Because G0J just goes also through all the elements of the group. So it's just a relabeling. It's just like a translation invariance for an integral or multiplying. Is it trivial for all of you? This? Yes? No? Say something. Because it's just a relabeling, okay? It's just because this is a bijection. This is a one-to-one correspondence. So this describes every element of the group. Any element of the group can be written as G0G. So I get all of them once, and it's perfect. Okay? So here I can do the same thing. I have the group of permutations of three elements, and instead of summing over these sigmas, I can always, so there is one special element in this group which is quite useful here. What have we done here? We have done a circular permutation of x1, x2, x3. If you look, it's xn, x1, x2, xn minus 1. Instead of x1, x2, x2, xn minus 1, xn. So there's a circular permutation. So it's useful to consider the circular permutation pi, which to 1, 2, 3 goes to 3, 1, 3, 1, 2. So it's a circular permutation. 1 becomes 3, 2 becomes 1, 3 becomes 2. Okay? And this sum, I can always rewrite it as a sum of exactly the same formula, but the abstract formula that I wrote. This is exactly the same sum, because these are all the elements of my group. This is the composition. You know that? Do you know what this means? The multiplication of two elements of the group. Okay? I don't know if you write it like that or not. Do you write it like that? If I have two elements of a group, of a permutation group, I just combine them. So it's a product, in fact. One, x2. And now you see it works well, if I didn't make a mistake. This will become sigma 3, if I'm not wrong. Otherwise you have to choose the other permutation. This will remain, this will become sigma 1, and this will become sigma 2. And now I have the right index, but of course the amplitude is not the same. And the identification is much easier. I think I've lost everybody, almost. Have I? Okay, so you can take it as an exercise. Do it by hand, just by hand. Okay? And you will see that in fact what you are really doing to make the identification is that you are identifying the amplitude for A sigma with Z1 to the power L, or Z sigma 3 to the power L, with the amplitude with A sigma pi, where pi is the permutation of three elements, the circular permutation. That's, okay, maybe the best way to learn that is to do it fully for the 3 case, just by writing the 6 terms, looking at who are the same, who are different, and 2 by 2 identifying them, and you will see that you will get a formula for the ratio of A sigma pi over A sigma, which is in fact given by Z sigma to the power L, Z1, Z sigma 3 to the power L. Because you see now the identification is automatic. By doing this trick, I have written the things exactly in the same way. And because it's independent, this guy, I mean times this one, has to be equal to this guy. Okay? So this gives me one more equation, one more ratio. But I told you before that all the ratios are fixed because of the cancellation condition, the two-body cancellation condition. All these ratios are fixed. So in fact, this gives me a constraint on the z's. This quantifies the value of the wave vectors, of the wave numbers. Z are wave numbers. Okay? And in the end, by putting all that together, I mean, I agree these things are quite heavy, and but you have to go through them if you, I mean, I think I give you enough exposure that if some of you I'm not even sure that out of 100 people, more than 3 or 4 may need it. I'm not sure. I don't know. If some of you need it one day, you'll have to go through it by yourself. There's no other way. I did it myself a few years ago when I needed to use that. Abhishek also, when you needed to use that. You have to go through it by yourself. But the purpose of all that is that maybe this will help you a bit to do it by yourself if one day you have to use it. I'm sorry, I could not do much better. But in the end, you will end up with equations which are of this form. Because you see this ratio is given now by z to the power L. But this ratio, you can compute it by making, this is a global permutation, pi, a circular permutation. But a circular permutation is a product of 2 by 2 permutations. And you know all the ratios of 2 by 2 permutations. They are given by these rational fractions that I wrote. P plus P minus P plus Q Z plus P plus Q Z1 Z2 divided and so on. So by breaking this ratio into elementary ratio, you will end up, I promise you, with the Bethe equations. So you will end up with these equations, valid for all z's. So again, I take P plus Q equal to 1 here. So these are the general Bethe equations. So there are n equations, n being the number of particles. There are polynomial equations. You can just chase out the denominator and put it here. And they are of degree of order L. L plus n, 2L. So they are, although they look a bit awful, it's a P, huh? Although they look a bit horrible, they are infinitely simpler than the characteristic equation for the Markov matrix. Infinitely simpler. And the nice thing is that they can be solved. I mean, maybe not always explicitly. And sometimes they can even be solved explicitly. But you can really work through these equations and obtain some precise results. So I think I still have 25 minutes, something like that. What? I'm sorry, I don't understand it. Minus? P? P? This? Yeah, I'm sorry, I have the, yeah. I'm like Fortran, I don't see the difference between upper cases and lower cases. So you're right, I mean, it's a small p. Yeah. Okay, I'm sorry for that. I have, yeah, this tendency of changing letters without, yeah, it's the same. Yeah, all the p's are the same. Okay, so now let's look a bit at these equations. Let's try to analyze them a bit. Any questions about that? So this is the whole procedure. I mean, when you have to do Bethe Ansatz, you have to go through that. But I promise you, once you have done it once or twice, you can go through it in less than an hour, half an hour. First time it takes a long time. To teach it, it's not so easy. But once you have done it, it's always the same thing. So okay. The first time is painful, but then it's okay. Z2, Zn to the power L is equal to 1. So So this corresponds to the global translation invariance of the system. This tells you that if you add L to all coordinates, all particles will be at the same place, so there is no difference. This is a trivial periodicity. Psi of x1 plus L, x2 plus L, xn plus L is psi of x1, x2, xn. Okay? So it means that z1, z2, zn is a nth root of unity. Okay, between 0 and n. Okay? But again, multiplying your wave function by z1, z2, zn adds 1 to each exponent. x1 will become x1 plus 1, x2 will become x2 plus 2, x2 plus 1, and so on. If I multiply my Bethe wave function by z1, z2, zn, I just shift all the x's by plus 1. Okay? So in fact, this is nothing but the translation operator on your system, and the exclusion process is translation invariant. So this just tells you that you can diagonalize translations whose eigenvalues are just Fourier modes together with your Markov matrix, and this is a kind of natural result that you should have these modes which are invariant. But this is just a global constraint on the z's. It doesn't tell you what each z is equal to. I'm not saying that each z is a pure phase. I'm not saying that each z is a root of unity. It's just a product. Okay? The z's have to be calculated by solving these equations. Yes? Okay, so these equations look horrible, but there are some special cases where they simplify. For example, the TASEP case. So in the TASEP case, q equal to 0 and b equal to 1, things become much nicer. The quadratic term vanishes, and you have only ratios of first degree polynomials, and you end up with equations of the type zk to the power L is the product of minus 1 minus zk over 1 minus zi. K equal to I equal to 1 to n, I different from k. It's much simpler. I can add I equal to k by putting a minus 1 here. Okay? Because if I take I equal to k, there's a minus 1, I just compensate for it. And I can, in fact, chase the denominator. So, in fact, I can put this thing together with this one, and the equation will look much nicer. Look like that. Zk minus 1, you can change the signs here, to the power n, zk to the power minus L is equal to minus the product of 1 minus zi I equal to 1 to n. So these are the TASEP Bethe Ansatz equations. What do you observe? So there is an equation for all k's. So this is an equation for k equals 1, 2, up to n. What do you see in these equations? So I have to write an equation for z1, for z2, for z3, for zn. And I have to solve them together. These are coupled equations. But what do you observe? You don't observe anything? This one? I'm just manipulating this one. I'm just putting this thing here, putting this thing here, mixing. It's trivial. Okay, just maybe I made a mistake in a sign, but I don't think so. So what do you see here? Well, there's something very nice which is happening here, is that if I write the equation for z1, z2, z3, of course the left-hand side depends on z1, z2, z3, and so on. but the right-hand side is always the same. It's just the product of all 1 minus the i's. So this is independent from k. It's k independent. Okay? So it means that somehow, in this very special case of TASEP, of course it's not true at all in the general case of ASAP, it seems that if you call this guy, you give it a name, call it Y for the moment being. Just call this Y. You just have to solve a one-body equation, polynomial equation, because this is a polynomial equation, in one variable, which I will call z. So you just have to solve the following equations. Z minus 1 to the power n, divided by z to the power l equal to y. Okay, and then, of course, you have to substitute the roots of these equations into y, because y is given self-consistently by this product, and you have to find the same value of y. So you see you have a kind of self-consistent procedure. You choose a y, you solve these equations for any given value of y, this will give you the roots, and then you substitute in this formula of y, and you will have solved the problem if, of course, after having substituted in this formula for y, you find the same y. So it's a kind of iterative procedure. Do you follow me with that? No? Not really? The key point is that this right-hand side does not depend. It's the same for all these. Okay? So I can give it a name, y, and say that I solve just a polynomial equation, a very simple, quite simple polynomial equation. And once I have solved it, all the z's are expressed as function of y's, of this y. I substitute it back here because I have a formula which relates y with the z's. It's a product of 1 minus zi. And of course it has to be consistent. And this gives you the solution of the TASEP Bethe equations. So maybe in the remaining 10 minutes, because this looks like a bit of black magic, but I will show you how to do it precisely, at least in one case. So you saw we already simplified by taking TASEP instead of ASAP in general. And there's one further simplification, is to take half filling. So L is the number of sites in the system, N is the number of particles. Half filling means that N is L over 2. Okay? So this will be half filling case. Yes? So L close to N, it's not so simple in fact. Yes, maybe, but yeah, but you see, if N is L minus 1, it means that you have only one hole in the system. So if you think in terms of hole, it's just a one-body problem. So you're right, it simplifies. But the nicest case is really half filling, which is in fact the most interesting also. It means that you have as many holes as particles in your system. It's a half density problem. So the nicest case is N, L equal to 2N. So L equal to 2N, half filling. Density is 1/2. L equal to 2N. And then this equation can be written in a much simpler way. I just have to, there's a nice change of variables. If I call, well, even that equation can be written in a much simpler way. In general, if I call zeta, so now, okay, all these things, they look coming from the hat, from from nowhere. These are educated guesses. I mean, when you work with these things, you try, and in the end, you find some nice ways of going through the problem. And it's not. You could proceed by keeping this variable, but it's much simpler sometimes to find a good change of variable. So if I call zeta 2 over z minus 1, I substitute in that equation. You see, I don't really like this equation because it's a ratio and so on. So it will really become a polynomial. It will become 1 minus zeta to the power n, 1 plus zeta to the power l minus n is equal to, so I substitute also on on the right hand side, and it gives you that. So of course each z, so it's zi. Now you see it's a nice polynomial equation, and again this thing does not depend on I. It's a constant right hand side. Of course. Yeah. And the eigenvalue, I forgot about the eigenvalue. Remember this eigenvalue which was p sum of 1 over z's plus q sum over z's minus p plus q times n. In terms of these zeta variables, it becomes just minus n over 2 plus half sum over zeta i's. So we have to solve this problem to find the spectrum of the TASEP on periodic system at half filling. And now here comes the nice thing. If I choose L and N in a half ratio, so L is, N over L is 1/2, then these two numbers will be the same. This will be N. L is equal to 2N. Okay? And this will just be equal to 1 minus zeta I square to the power n. Okay? And as I told you, this guy is independent a priori. I mean, a priori we take it independent. It is independent of I. So we shall do a self-consistent procedure that we shall call it y, compute the solutions of this polynomial for any value of y, and then adjust the value of y so that this is equal to that. But now we can really do it, because it's just, we have to solve a very, very simple equation. We have just to solve the following equation: 1 minus zeta I, but let's forget about the I, to the square to the power n is equal to y. Okay? But this we know how to solve it. I mean, this is just taking the nth root here. Of course, there will be some root of unity and not zeta. I can write it like that. This will correspond to zeta k. So you know explicitly how to solve these equations. We just have to take zeta k is 1 minus this thing square root. Okay? So I'm not going to do that because I think I don't have enough time, but I will show you what happens. In fact, something quite nice happens, and this is again the reason I'm teaching you that. Well, it's first because Sanjib and Abhishek asked me, but the reason is also because I think most of you don't really care about the exclusion process. I mean, why should you? But what's happening here is particularly simple. It's in fact the simplest model on which you can really work through with the Bethe Ansatz, but it's generic. What happens here also happens for all the models, or most of the models you can work through by Bethe Ansatz. So it's a good way to learn the procedures, the method, but also the solutions. So let's look at this equation. Okay? In fact, the equation before was, the complete equation was like that. is equal to y. Let's take the modulus of this equation. And now I have only positive numbers, so I can really extract the nth root, and this is 1 over n, and I can just call it y. Just notation, I mean it's something else. Or r if you wish, r. Let's call it r. So this tells you that the roots of the Bethe equations, okay, they lie on the curve in the complex plane. In the complex plane, they lie on this curve. 1 minus all the roots are on this surface, this curve in the complex plane. Do you follow me? Huh? Square is inside, yeah. Sorry. They lie on that. I just took the modulus. But this is in fact nothing but, unfortunately the square is inside, this. Okay? So the roots of the Bethe equations at half filling for the TASEP, they lie on such curves, where r is a parameter that we shall have to fix later, but okay. So what does this mean? I'm in the complex plane, I have the point +1, the point -1, zeta is in the complex plane. Do you know what these curves is? What are these curves? If I had a plus, what would it be? You know that. The sum of the distance to 2 points is constant. An ellipse. But I don't have a plus, I have a point here. So this is the locus of the points in the complex plane, such that the product of their distances to +1 and to -1 is a constant. Okay? So these are in fact classical curves which were studied 500 years ago, 400 years ago. They are called Cassini ovals. And in fact you know very well, well I hope at least in my generation we knew that one. In the case of r equal to 1, 0 is in sight. If r is equal to 1, 0 is a point such that the product of the distance is equal to 1. And it's a very famous curve called the Bernoulli-Lemniscates. You probably know this one. Yeah? The Lemniscate of Bernoulli? Have you heard of this thing? No? Never heard of that? This H-shaped, it's an 8. Okay? And for more general values of, okay, I thought it was a very famous curve. Poor Bernoulli. So if R is very, very, very big, extremely big, they will be very far from +1 and -1. It's a circle almost, okay? So it will look like that. If r is equal to 0, it's just either +1 or -1. If r is between 0 and 1, there are two non-convex components, two components. R equal to 1 is this one, and r bigger than 1 is this one. So the only thing you know is that the solutions of your exclusion, Bethe Ansatz exclusion process equations, they lie on these curves. Okay? And of course it's a polynomial of degree n, L, sorry. So there are L solutions, L roots. So let's take any value of r, let's take this one. I know that there are L roots which lie on these two curves. L is equal to 2n, and in fact if you do, then it becomes complex analysis, not very complicated. This is kind of high school, but you have to be slightly astute. You can see that in fact n of these roots are here. There are n of them on the right, and n of them on the left. as many. In fact, there is a simple symmetry. If in this polynomial, of course, if zeta is the root of this polynomial, minus zeta is the root also. So there is a symmetry with respect to the center of the diagram, of the 0 point, of the complex. So now we can state in very precise terms how to solve this equation, this self-consistence procedure that I told you before, which looked a bit unprecise. Now we can say it precisely. So the procedure will be the following. You take any value of y, which means of r, because r is the nth root, the nth. Yes. And I have all the L roots, and I have L over 2, which is n here on the right, and n over 2, L over 2, n to the right, to the left. Okay? But I have, so this will give me L roots. Yes? They're all in this curve. If I solve my equations, I will find them. And I can't solve my equation, I just have to take the, as I told you, I have to solve this equation. And this I can do. I just have to take the nth root of y and then take square root of 1 minus the nth root. Okay? If I call ym such that ym to the power n is equal to y, zeta is plus or minus. And I have to count how many I have and so on and so on. I will have 2n, and they will all lie on this curve. But now here comes the little tricky point. I don't need to have L roots. I need only n of them, half of them, because I have n particles on two n sides. Okay? So what I have to do is, among these two n roots, forget what's happening inside. Let's take the outer Lemniscates, or the outer Cassini oval. Among these two n roots, I have to choose n of them. Okay? So I have to select n points of this type on the oval. So of course the easiest case would be to select the n ones to the right. In fact, I have, how many choices I have? I have 2n choices. Okay? I have to select n guys among 2 n ones. In fact, 2n is exactly the size of the Markov matrix of the exclusion process at half filling. This is the number of states. So suppose I do a choice. So I choose this one, this one, this one, and so on. So I have a choice. I choose n of them. Okay? They are labeled like that. I choose n of them. Once I have chosen n of them, I can compute this ratio for a choice. For any given choice, I can compute this ratio. Do you follow me? It's almost the end. Don't worry. So I can compute this ratio. And this ratio, I compute it as a function of y, because I know all the roots as a function of y, or the nth root of y, but it's the same thing. Okay? So I can compute this ratio, and I can give it a name. This is a function. There's no, I call it like that. There's no special meaning to this name. I call it A0 of y, or A of y, let's say, A of y. Okay? So I make a choice, and I compute this ratio, which is a function of y. And now to fix the value of y, I have to solve the equation a of y equal to y. Do you agree? First, I observe that the right-hand side is independent of the value, the label of the root of my Bethe equations. It's always the same. So I give it a name, y. And I solve my simple polynomial equation, so simple that at half filling is just extracting an nth root and then extracting a square root. So it's completely explicit. It's here. I solve it for any given value of y. But of course, y has to be fixed. So how do I fix it? Once I have solved this equation, but of course I have too many solutions because I have only n particles, so I have a selection to do. I do any arbitrary selection of roots, and I compute this ratio as a function of y, which depends on the selection. And then, of course, self-consistently, this thing has to be equal to y. So that's the ultimate equation then one has to solve. Okay? So it looks a bit bizarre, but just one can take examples and even do it completely explicitly. If I take all the roots to the right, so all these roots here, so which means in fact taking no minus signs at all, okay, then this ratio can be computed explicitly. In fact, I was planning to do it, but I'm out of time. There is a formula for it. And again, this formula, of course, involves Catalan numbers. It really comes out. It's a simple series expansion with square roots. It's a simple formula. So I know what this is equal to, and then I have to solve this equation. And in fact, this will give me the ground state of the exclusion process, the one which is obtained sometimes by matrix ansatz. In the case of the periodic system, it's just flat measure. Now, I can make another selection. I take n minus 1 guys here, I skip that one, and I take this one. It's another simple choice. So people did say, and this is the important point I want to emphasize, so now there's a whole kind of vocabulary, poetry, which goes with it. If you choose the n roots here, it's like, don't ask me why, it's just a metaphor, but it's the same thing when you study Bose gas or XXY spin chains. It's like being in the Fermi sea or in the Dirac sea. And then, if you choose n minus 1 here, roots here, and take this one and skip this one, it's just like drilling a hole in the Fermi sea and taking one more root here. And this will give you an excited state. Okay? Then I can drill 2 holes and choose 2 roots on the other side, and so on and so on. And like that, slowly and slowly, you will build all the spectrum of the exclusion process. Okay? So you have this ground state which corresponds of taking all the roots on the right-hand side, and then you drill hole. Sorry? Well, in fact, it's not. It's not, because what happens is that it should be symmetric. Not completely. Equations, rotor density, Maiden perturbation, a very complicated paper, but very nice paper, and they obtained that. And in fact, you can even obtain they obtained a slightly more general result. Here we did it only at half filling, but you can obtain it for any density. So if you take a density rho, there will be a square root of rho 1 minus rho coming here. So probably the 2 was not here, because if rho is 1/2, this thing goes away. And there's an imaginary term also, which vanishes at half filling, 2 pi over L. And this imaginary term is also interesting because it tells you that the system relaxes with oscillations. And don't forget that you have to take the exponential of the Markov matrix. So this gives rise to terms of the type exponential minus t over L 3 over 2 plus 2 pi over L to rho minus 1 t. So these are oscillations. So they are wavy behavior, relaxation with some wavy behavior. This wavy behavior gives rise to correlations, spatial correlations in the system and time correlations in the system. And these wavy behaviors were very thoroughly investigated by Satya, by Mustansir, and Shamik maybe, I don't remember, and of course